Good day everyone, my name is Francesca Darlene Arcalulio, and in this video, I will discuss about noise, particularly its types, and also the noise equations. I will also demonstrate how to solve 10 problem-solving questions in order to better analyze the concept of noise in communications. So this video is divided into two parts, and in the first part, I will discuss the definition or concept of noise, its results, as well as its types. In the second part, I will discuss the different noise equations. And in order to have a better understanding about the concept of noise, I will demonstrate how to solve 10 problem-solving questions. So first, what is noise? Noise is an unwanted random addition to the signal. It is any unwanted form of energy tending to interfere with the proper and easy reception and reproduction of wanted signals. It is also defined as any undesired voltage or current that ultimately ends up appearing in the receiver output. So in here, we can see the transmitter and the receiver, and the signal is being transferred from the transmitter to the receiver through the channel. And in the medium, there is a noise present, and this noise enters the channel and interrupts the signal. Therefore, the signal that is received at the receiver end is distorted. So this noise is an unwanted random addition to the signal. So next, what are the results of noise? So first is the hissing or static, second is snow or confetti, third is echo or feedback, and fourth is bit errors. And eventually, it can also result to signal loss. So what are the different kinds of noise? So first, we have the correlated noise, which is mutually related to the signal and cannot be present in a circuit unless there is an input signal and is produced by nonlinear amplification. This means that if there is no signal, then there will be no noise generated. In an uncorrelated noise, it is present regardless of whether there is a signal present or not. So types of correlated noise. First, we have the harmonic distortion. It is an unwanted harmonics of a signal. It is the deformation of a waveform by unwanted multiples of an original frequency, as we can see here in this graph, causing interruptions to the way the waveform behaves in electrical circuits or sounds, in the case of music and sound waves. Second is we have intermodulation distortion. It is the generation of unwanted sum and difference frequencies, or what we call cross products, when two or more signals are amplified in a non-linear device. So next, we have the types of uncorrelated noise. First is external noise, which we will focus on later in the video, and it is generated outside the device or outside the receiver circuit. Second is the internal noise, which is generated within the device, as its name implies, or within the receiver circuit. So next, we have types of external noise. So external noise is defined as the type of noise which is generally externally due to communication system. So they are analyzed qualitatively. Now, external noise may be classified as first, atmospheric noise, also known as static noise, which is in the natural source of disturbance caused by lightning, discharge in thunderstorm, and the natural disturbances occurring in the nature. Second is industrial noise, which are caused by automobiles, aircraft, ignition of electric motors, and switching gear. So its main cause is high voltage wires. Third is extraterrestrial noise, which exists on the basis of their originating source. They are subdivided into solar noise and cosmic noise. So fourth, we have the man-made noise, which is generated by man. Next, we have the types of internal noise. First is the shot noise. So this noise generally arises in the active devices due to the random behavior of charged particles or carriers. In case of electron tube, shot noise is produced due to the random emission of electron from cathodes. Second is partition noise. When a circuit is to divide in between two or more paths, then the noise is generated is known as partition noise. The reason for the generation is a random fluctuation in the division. Third, we have the low frequency noise. They are also known as flicker noise. These types of noise are generally observed at a frequency range below few kilohertz. Second is high frequency noise, also known as transit time noise. They are observed in the semiconductor devices when the transit time of a charged carrier while crossing a junction is compared with the time period of that signal. And lastly, we have the thermal noise. Thermal noise are random and often referred as white noise or Johnson noise. Thermal noise are generally observed in the resistor, or the sensitive resistive components of a complex impedance due to the random and rapid movement of molecules, atoms, or electrons. So next, we will move on to the noise equations. First, we have the noise power. So the average noise power in watts is directly proportional to the temperature of the conductor in kelvins and the bandwidth of the noise spectrum in hertz. So the average noise power, which is denoted by P sub n, is equal to the Boltzmann constant times the temperature of the conductor in kelvins times the bandwidth of the noise spectrum in hertz. Next, we have the noise voltage. So the RMS noise voltage, which is denoted by V sub n, is equal to the square root of 4 times the Boltzmann constant times the temperature of the conductor in kelvins times the bandwidth of the noise spectrum in hertz times the equivalent noise resistance in ohms. Second, we have the RMS noise voltage due to several sources. So in series combination, we have Rnt is equal to Rn1 plus Rn2 and so on. And in parallel combination, we have its reciprocal. So the total noise voltage, which is denoted by V sub Nt, is the same formula for series and parallel. So next, we have the power spectrum density, or what we call the noise density. It is the average noise power per hertz of bandwidth. It is a figure that determines the amount of noise contained in a specified bandwidth. So N naught is equal to P sub n, the average noise power all over the bandwidth, and it is also equal to the Boltzmann constant times the temperature in kelvins. So next, we have the signal-to-noise ratio, also called as SNR. It is a relative measure of the desired signal power to the noise power, and we can see that S, which is the signal power, all over N, which is the noise power, is equal to P sub S all over P sub N. Okay, so this is the graph of the signal-to-noise ratio, and we can see that the average signal power is all over the average noise power is equal to the power, or S over N. So SNR power is equal to SNR voltage squared. So the signal-to-noise ratio relationship between the power and the voltage can be seen in this equation. So we can also express it in decibels. So we know that in power, the signal-to-noise ratio in decibels is equal to 10 log of 10 SNR of power in terms of watts, and SNR in decibel is equal to 20 log of 10 SNR of volts in voltage. So next, we have the noise factor F. So F is equal to the SI all over NI all over S naught all over NO. So it is the ratio between the input signal noise ratio, SNR, and the output signal noise ratio, or in other words, the SNR with the additional amplifier and the SNR without it. So we can see that the noise figure in dB is equal to 10 log of the noise factor, and this noise factor is equal to the ratio of the input signal noise ratio, SNR, and the output signal noise ratio. So these are all in watts, and the noise figure is in decibels. So next, we have the equivalent bandwidth. The equivalent bandwidth to be used in noise calculations with reactive circuits is denoted by this equation. So the equivalent bandwidth, denoted as B sub EQ, is equal to pi all over 2 times the half power bandwidth in hertz, which is denoted by B sub 3 dB. So next, we have the equivalent noise temperature. T sub EQ is equal to the reference absolute temperature, which is 290 kelvins, quantity times the quantity of the noise factor minus 1. So next, we have the noise due to amplifiers in cascade, as we can see here, and overall noise factor of n stages is equal to this equation. So that's the noise factor, and overall noise temperature of n stages is denoted by P sub EQ, and overall noise resistance is denoted by R sub EQ. And we have the following equations, where A, we can see here in the overall noise resistance, is equal to the voltage gain ratio, and G, which we can see in the denominator of the overall noise factor and overall noise temperature of n stages, is the power gain ratio. Next, we have the shot noise. So it is a form of internal noise which is due to the random variations in current flow in active devices such as tubes, transistors, and diodes. So I sub n, which is the RMS noise current in amperes, is equal to square root of 2 times the bandwidth over which the noise is observed in hertz times the DC bias current in the device in amperes also, and times the charge of an electron, which is 1.602 times 10 to the negative 19 coulombs.